He's going to talk about peaceable queens.
Okay, thanks Ben. Thanks everyone for coming. It's always a pleasure to be back in Korea, seeing so many familiar faces. So let me just say this isn't really my research area. Maybe I say that with every talk I give. But I think this is a very cute problem. Sometimes you have to have a bit of fun in life. So let me tell you what the problem is. So what we want to determine is this number an, and an is the maximum number of white queens and black queens that you can put on a chessboard. So the number of queens is the same, such that no queen can capture a queen. Oops, that's bad. Okay, it's back. Right, so that no queen can capture any other queen of the opposite color. So the white queens can attack each other, the black queens can attack each other, but no white queen attacks a black queen. So I'm just going to go super slow. Just so everyone is on the same page. Okay, so for people that don't play chess, like queens are pieces that attack like horizontally, vertically, and diagonally. All right, so let's just compute this number for some small values of n. So we have n, and we have an. Okay, so I guess the smallest case is if we have like a 1-by-1 board. So okay, in a 1-by-1 board, you can't even fit the queens on. So for n equals 1, the answer is 0. Okay, let's move to the 2-by-2 board. So again, okay, so maybe I'll use red and blue. So in this case, once you place like a red queen,
we want the nice queen symbol.
The queen symbol, okay, maybe we do something like that thing like that. So once you place, let's say, a red queen, then it already attacks, right, all of the other squares. So you cannot place like a blue queen anymore. So the answer for 2 is also 0, right? Okay, so let's go to 3. So we have the 3-by-3 board. Okay, so if you're not very smart, like maybe you place your queen in the middle, and if you do that, then it already attacks like every other square. So you won't be able to place a blue queen, but you know, if you place it in a corner like that, then there's a place to put like a blue queen. So you can place a blue queen there, for example. And so these two are non-attacking, and it's easy to show that you can't do better than this. So okay, there is a reason I'm computing these values, so just bear with me, right? So okay, so let's go to 4. So there's lots of solutions for 4, but I guess you kind of have the idea that it's good to put these things like in the corners or like at the border, because that's like when you attack as few squares as possible. So one solution you can have for n equals 4 is to put 2 of the red queens like in the corner. And then now you're lucky because there's like 2 squares for the blue queens. So you can put the blue queens like here. Okay. So now we have 2, and then it's easy to show that you cannot do better than this. Okay, I'm gonna keep on going. There is a reason I'm doing this. Okay, so let's go to the 5-by-5 board. Okay, so does anyone have a guess what the answer is for 5? Yes, so 4?
4 queens in total, so
4?
Oh,
Sorry.
I guess 4 red and 4 blue.
Yeah, okay. So how would you do it?
Put the red in the outside corners and the blue.
Okay, yeah. So if you put the reds in the corner, then you're kind of lucky because the unattacked squares are precisely like these ones here, right? Okay, these are no longer queen symbols, but with me. So this is a solution for 4, and it turns out you can't do any better. Okay, so 4. I'm going to keep on going, as I have a reason to do this. So let's go to the 6 by 6 one. 1, 2, 3, 4, 5. Is this right? Okay, I won't torture you, but I guess I'll just show you the solution. So it turns out you can do 5. So let's put the queens here, like this. Oops, make it like this. And let's put the red queens here. Okay, I hope this is right. So if we quickly check, like no blue queen attacks like any red queen. This is a solution with 5. And it turns out it's the best you can do. Okay, I'm only going to do one more, right? So let's do
What, you
7.
can't stop at 7?
7, I think, is hopefully enough. So let's go to 7. 3, 4, 5, 6, 7. Okay, so again, I won't torture you, but I'll just show you a solution. So I think you can color these 3 red, this blob red, so this is 7, and then you can color things like this and this L. So you can kind of easily check that no blue square attacks like any red square, and there are 7 of each. Okay, so these are some small values. Okay, so the reason I did this is because, okay, there's a resource that probably most of you guys know about. It's called this online encyclopedia of integer sequences, and it's a pretty cool resource. So let me just close my talk now and go to it. So basically what you can do is put in like a sequence of numbers, and this website will tell you like if your numbers like mean anything, right? So so in this case we kind of know what these numbers mean, but this encyclopedia will kind of tell you everything you would want to know about the sequence. And it could be that maybe these numbers like count something else as well. So it could be that you think you're counting this Peaceable Queens problem, but maybe they also count something else that's interesting. Or maybe these numbers are like coming from some aliens, right? You don't really know what they mean. Some aliens are sending you some signals, and you want to know if they mean anything. So let's try. Okay, so I'm gonna put in like 0, 0, 1, comma 2, comma 4, comma 5, comma 7, and I'm gonna search. Okay, so you see that there are some sequences. This is like sum of exponents and prime power factorization of, oops, can you please come back? Okay, so that's not us. This is some Fibonacci stuff, that's not us. But this third entry is precisely what the talk is about, right? So this is Peaceable, coexisting armies of queens. And it gives you some more values. It also gives you like further information. And you'll notice that this has a very interesting sort of sequence number. It's like A 250,000. And that's because like the founder of this online encyclopedia, Neil Sloan, like loves this problem. So he kind of made it so that this sequence got the special number 250,000. And I learned about this problem so I think this is also listed here, on a YouTube video. So there's a channel on YouTube called Numberphile, and Neo Sloan gave a talk, sort of a short video, introduction to this problem, and it's a lovely video. I encourage you to watch it. Like, he's kind of so enthusiastic about this problem, and that's how I learned about it. And in here you'll actually see we should exist, I think, somewhere. Do we exist? yeah, we exist. So we are here. So our paper is also like listed among the information for the sequence. Okay, so that was just some introduction to this online encyclopedia, something you should know about and use. Okay, let's go back to the talk. Here. Okay, so right, so let me tell you sort of some more motivation for the problem. Let me slide this up here. So other people have sort of thought about this problem, and it turns out that it's sort of a benchmark problem for like various optimization methods, such as integer programming, SAT solvers, logic programming. So these are different ways to solve the problem, and we kind of use it as a benchmark to say, okay, what's better, like a SAT solver or an integer program. You don't really need to know what all these things are. Maybe I'll just tell you what one of them is, right? So there's a way to solve this problem just as an integer program. So this just means you have some variables that are allowed to take integer values. I don't know why this thing is turning off. Okay. And you can have some linear constraints. So let me just write out this IP formulation. So your variables. So basically you'll just have like some decision variables that tell you like whether you'll place a white queen like on a specific square, right? So you have variables wij and bij, and they're like 0, 1, right? And so I guess I and j go from like 1 to n. This is the normal way to index the squares on your board. And this wij will be like 1 if you're going to place like a white queen like on that square. This bij will be 1 if you want to place like a black queen on that square. And then you can just write out exactly what you're trying to maximize. So you just maximize. So the sum of the wij is just the number of white queens. And then you have some constraints that are given by the problem, right? So subject 2. So, you know, the sum of the number of white queens is just equal to the number of black queens. This is just some constraint that you'll write down. And then you want to write out constraints that encode that, okay, you cannot have a white queen and a black queen in the same row, for example, right? So maybe I won't write out like all of them, right? But one of the constraints would be that, let's say, wij plus bik, that should be less than 1, right? So this would be like for all I, j, and k. Right, so this constraint just says, okay, you should not have a white queen and a black queen in the same row, right? Okay, and then you can do this for the columns, and you can do this for the diagonals as well. Okay. Okay, so that's the IP formulation, and you can also formulate this as a set, like as a set solving problem or logic programming, and so it's sort of a benchmark problem. Okay, and for each one of these ways to model the problem, there's like more than one way to do it. So it's also like a benchmark problem for symmetry breaking constraints, right? So this means that the problem has a lot of symmetry. So for example, black and white are basically symmetric, right? You can switch them. There's also symmetries of the chessboard, like rotation. So rotating would turn like rows into columns and vice versa. So you want to introduce some constraints that like break the symmetry, right? And some symmetry breaking constraints are better than others. So this is sort of a benchmark of what kind of symmetry breaking constraint should we use to solve the problem as fast as possible, right? Okay, and then I put in it's fun. So if you don't care about motivation, I think it's just a cute problem. Okay, so that's enough for motivation. So we also want to solve the problem on the torus. So on the toroidal board, it's chess, but the board sort of wraps around itself, right? So this is like Pac-Man. This is the same as the other side, and the bottom gets identified with the top. So you're playing like on the surface of a donut. This doesn't really affect like the rows or the columns because it's like the same attacking, but the diagonals sort of become different, right, on the toroidal board. So for example, like this diagonal here on the regular board would just be this part, but on the torus you kind of attack further, right? So you come out on the other side, and then from there you go back there, right? So we also want to solve the problem on the toroidal board. Okay. So I won't make the table on the of the torus, but this is also another sequence that's in the online encyclopedia. Okay. Okay. So I have to go back, I think. Go back. Okay, so let me tell you the sort of known results. So let's start with the regular board. So you might think that to solve the problem, it's like useful to put the queens at like the boundary of the board, and this turns out to be true. So there's a construction that has like 4 blobs. It's called the Amy construction. So you place like white and black queens like that. And this is a construction that works for all n, and if you count, you cover like quite a few squares, like quadratically many, and it's like 7/48 of the total number of squares, right? So, so this is a construction that gets you 7/48 n squared white queens.
So this is the regular board of the torus?
This is the regular board, okay? Because you can kind of see that like on the torus, like these would like go out this way, come out through the top, and attack here, actually, right? So it's clear that the answer for the torus is like less than the answer for the regular board, just because, yeah, like you can think of this as a hypergraph coloring problem, and these hyper edges are just bigger, actually. Okay, so that 7/48 is about 0.1458, and then the best upper bound we knew was just a quarter n squared. So there's a pretty big gap between this lower bound construction and the upper bound. Okay. So, and for the torus, not much is really known. So, so the exact values have been computed up to n equals 12, but okay, Sebastian looks confused. But there is no like lower bound construction. There's no upper bound. There is a curiosity that, like this 8x8 board, you can put more queens than on the 9x9 board. So that seems kind of weird at first, but if you think about it a bit longer, on the torus, right, it's not true that you can embed the n by n torus like into the n+1 by n+1 torus. So on the regular board, this is true. So this sequence an is definitely monotonic. It shouldn't go down. But on the torus, this is not true, actually, right? And it turns out that, in fact, yeah, like on the even board, this T8, you can pack more queens than on the 9x9 board. Okay.
Is it always true that if you go up by 2, then if you just look at, say, the even boards only, then you have 9?
This we don't know, and so I'll say more about this later, but even if you look at the odd sequence, like we have found some construction that seems to have more once you go up, or seems to have less if you go up by 2. But we don't know if
Right, if it's the best
if it's the
possible.
best one. It's the best ones that we've found.
Yeah, yeah.
But yeah, I'll say more about that after.
So if you relax the program, what would that give? Could anyone consider that? To any
The LP.
real between 0 and 1?
Yeah, so you could do that, but it's a bit unclear what these fractional like solutions will give you, actually, right? So this is a way to prove lower bounds, actually, right? Every solution here will give you like a feasible placement. So yeah, this I'm.
Maybe you could just take 1/2 for every variable.
Yeah, you can do. Yeah, maybe. Yeah, if you took a half to yeah, you might place half a black queen. Yeah, so you would satisfy these constraints, I guess, right? If you placed half a black queen and half a white queen in every box, you would satisfy these constraints, because you would add up to 1, right? So you would get a pretty bad bound of, yeah, like half of n squared. Right, okay. Okay, so I guess this thing is sort of dying quickly. I don't know why. Maybe I can change the settings or something, but whatever. Maybe I'll just change the page faster. Okay, so what we proved is a better upper bound for the regular board. So we get this 0.1716 n squared. So you see that this is, quite a big improvement over this 0.25 n squared. And in fact, like, the proof of this 0.25 n squared actually doesn't use the fact that like queens can attack diagonally. So this bound holds for like peaceable rooks. Rooks are just pieces that move like horizontally and vertically. And for peaceable rooks, like it's actually tight, right? Because you can actually place a quarter of the squares, right? So our proof like definitely uses the fact that queens can attack diagonally, right? Okay, and then we get some bounds for the torus. So so for the even torus, we get this. Okay, I don't know why. Should I fix this?
This is some mechanical issue.
Okay.
It seems like it's getting faster and faster.
Yeah, maybe. Should I just stand here? I don't know. Okay, I'll just keep on talking. Okay, so. Okay, so so for the even torus, we get these bounds. So our lower bounds are given by explicit constructions, which I'll just show you, and our upper bounds. Okay, I'll tell you how we prove the upper bounds later. And then we also get things for the odd torus. There it's not quite as good. We have a bigger gap, and if you're perceptive, you notice that these numbers, so like our lower bound for the even torus is right. So our lower bound for the even torus is actually higher than our upper bound for the odd torus. So our bounds are good enough to show that these two sequences actually diverge, right? So we actually show that there's a quadratic separation between like this odd sequence and this even sequence, right? So, so the even sequence is bigger actually, right, by a constant times n squared. Okay. Okay, so let me continue. Okay, and then we also have an algorithm. The algorithm is okay. is blue. Okay, I'll just keep talking. So the algorithm is not that complicated. It's just like a local search algorithm. And we've also implemented it. So we've implemented as like an app that you can run in your browser. So if you're interested in the problem, like after the talk, you can just open your browser, go to the website, and run the algorithm and play with it. There's a QR code that you can also scan that will take you to the website. I mean, this is a thing that people do now. I don't know why. I mean, I guess the QR code is not there, but.
Sorry, what is algorithm for?
What is that?
What is algorithm for?
The algorithm is just for computing, well.
Upper bound or lower bound?
It computes, so the algorithm computes lower bound, so it finds solutions which seem to be optimal. Like we don't have proofs, but for example, for the regular board, it finds this Ainley construction very quickly, actually. We didn't find anything that is better than the Ainley construction, so this gives maybe some evidence that like this construction is optimal. But we couldn't really like prove anything about the algorithm, except that like it seems to be fast and that the solutions it produces are of high quality. Okay, something is happening. Okay, so that is the website, and that's the QR code, so like you can just scan it, and I guess it will take you to the website. I'm gonna try to like live demo the app like during the talk. We'll see how that goes. So yeah, so this is just, and I mean the approach is robust, that it works both like for the regular board and for the toroidal board. So like you'll see that the app has a button that you can switch between the torus and the regular board. Okay. I'll probably still finish early because I think what we did was not terribly deep. So we'll see how things go. Okay. So let me just start with the lower bounds. So as I said, these are just given by explicit constructions. So this is the construction. We call it like a plaid because it kind of looks like a plaid t-shirt. So the plaid kind of has like two parameters. Like this 8 is like the length of that like topmost corner there, and the 10 is like the width of the topmost corner there. And it's easy to check that this, so in the paper we just explicitly give the coordinates of the plaid, and it's easy to check that it is,
What is
the 10 is like this length here, and the 8 is this length.
Oh, I see. So
They don't need to be symmetrical.
They don't have to be the same, right? And you can, so any one of these is actually a valid construction. And so to get the best possible lower bound, you basically just have to solve a quadratic, right? Because like you can choose these parameters so that like the number of white queens is pretty much as close as possible to the number of black queens. And that you can kind of count, right? Because if you kind of think of this as like a continuous problem, the fraction of squares covered here is about 1/4 of like this area, right? The fraction that's covered in that top leftmost square is like 1/2 because every other thing is covered. Here, that's 1/4 of a rectangle, and that's 1/4 of a rectangle. So the bound is just like got by solving some quadratic equation. That's what that number represents, this 0.1339. And there is sort of an error of like a linear error in n, that's why you just get this sufficiently large n part, right? So that's it. It's not terribly deep, right? So let's move on. So this is the construction for the odd torus. It looks different than the even torus. So we call it like the Argyle. So Argyle is kind of like this diamond-shaped pattern if you're like a fashionista. So again, like in the paper, we just give explicit coordinates for what this thing is. And in fact, like it is a solution. You can check that easily. And kind of the only thing to check is like, well, how many squares are actually covered? So you can do that by sort of this proof here, right? So maybe I'll just say it instead of writing stuff on the board, right? So again, it's kind of useful to think of this as a continuous problem. So we split up this board into like 36 triangles here. All of these triangles are congruent. And you can kind of check like the density that's covered by white and by black, right? So up to like a linear error in n, the white queens cover like, so how many triangles do they intersect? Like 1, 2, 3, 4, 5, 6, and 6 on that side, so that's 12. And up to an additive error, they cover like a quarter of the squares, right? So, so basically, we get like a quarter times like this 12 over 36, right? That's the density that's covered, and this is like 1/12. Okay, and that's exactly what this number is. 0.0833 is just 1/12, actually, right? So that's the odd torus construction. What am I doing? Oh, okay. So, so let me kind of, it's useful to think of this maybe as like a hypergraph coloring problem, right? So let's think of a hypergraph whose vertex set is the set of cells. So this notation n just means the numbers from 1 to n. So this is like all pairs ij, the natural indexing of these cells. Of course, there's like two ways you would want to index this. Some people use like the matrix notation, and some people use like the Cartesian coordinates, right? So, okay, like, is this 1, 1, or is this 1, 1 for you, right? Like, okay, so in the paper we use like matrix notation, but it doesn't really matter, right? So, so this is a way to do this using hypergraphs. So the hyper edges will be like the rows, the columns, and the diagonals. There's kind of two sorts of diagonals. So anyway, this is a way to say something is a row, right? It's something of the form like I cross n. These things are the columns, right? The diagonals you can also say algebraically. So the diagonals are the things that have like constant difference, right? So where I minus j is a constant, right? And the skew diagonals you can say as the things that have a constant sum, right? So where I plus j is a constant, right? And then you can also say what diagonals and skew diagonals are on the torus. So this is like for the regular board. But for the torus, it's basically exactly the same thing, except you work like mod n, right? So the way to write the diagonals is that their difference is a constant mod n. And same thing for the skew diagonals. Okay, so then now you have a hypergraph. Like, so for the regular board, you would take that set of vertices, you would take the rows, the columns, the diagonals, and the skew diagonals. And then now you're looking just for like a partial coloring of the vertices, like red and blue, let's say. The same number of vertices get colored red and get colored blue. And then no hyperedge should have like a red and a blue vertex, right? That's one way to just say it using hypergraphs. And then for the torus, you would use like rows, columns, Zn diagonals, and Zn skew diagonals as your hyperedges. Right? Okay, so this is a useful thing for the formulation that I'll do. But let me at least first say, like, this explains like why there's a difference between the odd torus and the even torus. So once we see the definition of these hyperedges, you'll note that the even torus like enjoys a property that the odd torus doesn't. So let's say a set is parity consistent if the sum of those indices is always the same parity, right? So if I plus j is always the same parity as k plus l, right? For any two pairs in the set. And it turns out that on the even torus, like these diagonals like always are parity consistent, right? So this is the reason why these two constructions look quite different, and why you can kind of pack a lot more on the even torus than on the odd torus. Okay, okay, so now let's go to the upper bounds. I didn't say how we do it. So the main idea is to formulate the problem as some, like non-linear optimization problem. So this was this IP that I didn't finish, with like only a constant number of variables. Okay, so in this integer programming formulation that I wrote, this was a way to get lower bounds actually, but it's like dimension dependent, right? So like the number of variables grows as the board size like grows, right? But we want to do something somehow where the number of variables is the same for every single board, okay, right? So I'll tell you how to do that, right? It's not so complicated. So, so these are the variables that we were going to use. So we'll have a variable for the rows, that's like the R, the C, we'll have a variable for the columns, for the diagonals, and the skew diagonals. So the simplest this nonlinear program will be for the odd torus. So this is the one I'll explain now, but they're all pretty similar. So I'll just start with the odd torus and explain how to change it for the even torus and for the regular board, right? So, so for each of these sort of dimensions, like row, column, diagonal, skew diagonal, we're going to let this variable yx be the fraction of squares, so we divide by n squared, that are attacked like along that dimension, right? So we've placed the white queens, and this y sub r, for example, is the fraction of squares that are attacked along rows, okay? And this y sub c is like the fraction of squares that are attacked along columns, right? That's actually pretty easy to compute. It's actually just the fraction of rows, for example, right? So if you cover half the rows, you actually attack like half the squares, right? Okay, so that's those variables. So we have like this Venn diagram. So this is sort of like a Venn diagram nonlinear program. So so we have these blobs for like columns, rows, diagonals, skew diagonals. And we'll also have like variables for every region of this Venn diagram, okay? So there should be 16 regions actually, but like because I use circles to like represent like these things, there are not actually 16 regions here because there's only 14, but anyway. So we'll have these variables that represent like the different regions of the Venn diagram. So for example, there's a region that is like the intersection of like of D, R, S, and C, right? These four sets. And then there's also the outside region. That's something that's in none of them. Okay, so those are the variables we use, and we want to also just count like the fraction of queens that are in each of these regions. Okay. So now that we know what these variables mean, we can just write out like what constraints must be satisfied. So first of all, if we go back to this Venn diagram, we notice that the intersection of all of these four guys is precisely where the white queens are, actually, right? So if you're a white queen, you are in the intersection of all four of these sets, right? And that's exactly like the condition to being a white queen, right? And so the white queens are the ones that are in this intersection, and actually the black queens were allowed to place in the outside region, right? Because if I'm not attacked in any one of these four dimensions, that's a legal place to place a black queen, right? So with that in mind, what we want to do is to maximize the minimum of those two areas, right? The intersection, that's like the Z of the intersection, and the Z of the complement, right? Everything that's on the outside. So that first variable represents the number of white queens. That second variable represents where you can place the black queens, right? And then there's just like simple constraints that are satisfied, right? So the sum of the Z's better add up to 1 because there are fractions of squares. And then we have some kind of normal constraints. Those things don't really say anything. This is basically a definition, so I'm also interested in the intersection of, let's say, the rows and the columns, right? So I just introduce a variable that like represents this region of the Venn diagram, a union of these smaller regions. And I guess the key constraint is like this like quadratic constraint here that's like pretty easy to see. So basically, if you have, let's say, rows, so maybe you have these rows that cover maybe like a quarter of the squares, right? And then you have, or sorry, this is columns. And then maybe you've got columns that cover, let's say, a third of the squares, something like that. Let's make this bigger. I don't know. Wait, what did I? This looks like a half now. Anyway, let's go with a half. It goes this way. Then this intersection is like multiplicative, right? The squares that are covered by like these rows and these columns is like 1/4 times like 1/2. This is 1/8. Right? So you get this quadratic constraint here. And on the odd torus, this is also true for like rows versus diagonals, actually, right? So for example, if the picture sort of looked like this, where you have like some squares by rows, and you've got some diagonals that maybe look like this, then this area here is like multiplicative, right? It's basically the product of like this width times this width here, right? This is true on the odd torus, but not on the even torus, actually.
For diagonals versus rows?
Diagonals versus diagonals, this is also true. So,
Like,
so you can also have something that looks like this, let's say, and this area will be the product of those densities.
so this is where the difference between odd and even
Yes.
torus, isn't it?
Yes.
Yes. But for when you have a diagonal and a row, is there a difference here?
Right. So not really. So it's the same. Yeah. Okay. So okay. So these are just the constraints. The only non-trivial one is just this quadratic constraint between intersections, right? Right. So this is some nonlinear program, and all we do is like we just plug it into our favorite like solver that does this for us. Actually, this one we did by hand. So you can solve this by hand if you want. And it outputs like 0.125 n squared, right? So this is an upper bound, but this is also what the computer spits out, right? So I should say that, so these results were accepted to some conference called ALANX. This is Algorithm Engineering and Experiments. And they give badges that like certify your results, right? So like, okay, so this just like, these results have been certified independently. So just trust me, they're true. So yeah, you get this 0.125 n squared just by computer. Okay. So you can do like a similar thing for the even torus. It's slightly more complicated, but not much more complicated. Let's go here. So let me kind of just explain the differences. 6. So I guess on the even torus, like you can look at the checkerboard coloring, like the normal checkerboard coloring of the chessboard, this one. And like on the even torus, like the diagonals actually stay on one color, actually, right? So on the even torus, like a diagonal will either be black or it will be white, actually. So you don't get this nice intersection property that you get on the odd torus, because, I mean, if you take like white diagonals, they will never intersect like black diagonals, right? So that's like one difference. You have to refine the hyperedges to white and black diagonals. That's kind of what I won't tell you what that thing is. And then the intersection between diagonals is a bit different as well, right? So for example, if I take this black diagonal here, right, and I choose like another diagonal, maybe I choose this diagonal, so this comes out like here. So you'll notice that there's actually like 2 squares that these diagonals intersect in, this one and this one, actually, right? So whereas like on the odd torus, they actually intersect in 1 point. On the even torus, they intersect in 2 points, actually, right? So it is like kind of multiplicative, but you also have to like multiply by 2, right? That's like the only difference. So it's the same, like, it's pretty much exactly the same nonlinear program, but you have to split it into black diagonals and white diagonals, and then you have this constraint that says, okay, like if you intersect black with black, you get like 2 times their product, right? So again, and then we don't want to think to solve it, we just put it in a computer. Oh, sorry, this is the regular board. I don't know what happened. Oh, wait, do I go back? Okay, I should finish soon, I suppose. Okay, let me speed up. So this was the odd torus. This is the even torus. The regular board is even more complicated because the diagonals don't all have like the same length. But there's a key lemma that we prove, like human proof, right? So this is just something that's true, whatever. You don't have to read it, but this lemma proved by humans implies like a constraint you can add to the nonlinear program. It is this constraint here. But it doesn't really matter, right? So it's the exact same thing. And we just feed it into a computer, and the computer spits out this 0.1716, okay? But I guess like if you can think of any other constraints that these sets should satisfy, we can put it into our HAL 9000, and maybe it will like get a better bound, actually, right? So for example, like we didn't have anything that has things about like triple intersections, right? Like rows versus columns versus a diagonal, for example. Okay, so that's the regular board. Let me quickly describe the algorithm and then demo the app and then finish. So the key idea of the algorithm is swapping. So we have some kind of configuration already, and there's an imbalance. So you can see, like, this is actually a screenshot of the app, or an early version of the app. So there's like 36 white queens and 29 black queens. And this swapping is just to choose some row, some column, or some diagonal. In this case, it's diagonal, and just to perform a swap, right? So the swap means delete all of those squares from the larger of the two. So in this case, it's white. So we'll just delete it from white. And once you delete it from white, that will open up some squares that could become black as well, right? So in this case, it's like this square, that square, and that square, right? So that's all. It's just a local operation. And this is sort of the key concept in the algorithm. It's not really that complicated. We start with some random assignment of white queens. Let's assume that there's fewer white queens than black queens. And then we just do a swap to increase the number of white queens, right? We also do something that's like maybe counterintuitive. So remember, like, we really only want to maximize like min of white and black. But it turns out that it is useful to increase the total number of queens at some steps of the algorithm. So this might even make the min smaller, but we found that sort of globally it makes the algorithm perform better, actually. So there's some steps of the algorithm that increase the total number of queens by swaps. So we just repeat this. Okay, let me. Should I live demo? Okay, let's forget the live demo. You can you can go scan the QR code. What I do want to show is just what the algorithm found for the odd torus, right? So it turns out that the algorithm finds solutions that are like a lot better than our lower bound construction, right? So the only problem is that, like, as humans, we couldn't see the pattern like amongst these solutions that we found. So I'm gonna show them to you in the hope that like someone spots like what is going on here. So I'll just go through them quickly. So this is for n equals 13, like there's like 16 queens each. This is n equals 15, 17, 19. So it's kind of like random what's happening here. This is n equals 21, 23. I do find them quite pretty pictures.
Are you trying making close with them?
Like, yeah, I mean, yeah, I don't know. Like we should, there are some like curious things that happen. So I'm just gonna keep on going. So 41, 43, 45. So you'll notice this is a curiosity here, where, so for n equals 51, like our algorithm found like the solution with 252 queens each, but for n equals 53, it could only find like 250. So even for this odd sequence, it might not be monotonic. Like we don't know actually. And then like weird things start happening. So you can see like this thing looks sort of way different than this solution here, right? We have some leaves or something here. And this is 61, and we kind of stop at 63, right? So let me just end with some open problems. So the first one is just like, what is a conjectured answer even for the odd torus, right? We don't even have a candidate for what the answer should be. Maybe there's some number theory involved here, like it could subtly depend on like the prime factorization of n, right? But anyway, if you see a pattern, let me know. And then, okay, like we suspect that our lower bound construction for the even torus is essentially optimal. So we think this is the answer. It's not quite the answer, so you can actually do a swap to increase the number by 2, basically. So we have a conjecture that the answer is probably our lower bound construction up to an additive constant of 2, let's say. And then lastly, like, okay, is this Ainley construction optimal, right? So one way to prove this would be like to add more constraints to our nonlinear program, for example, right? Okay, so let me stop there. Thank you.
So any questions?
Oh, there's a...
What's your result with constraints? Do you know that it will give an answer that is given the lower bound, or is it just a heuristic that...
It's kind of, yeah, we can't prove anything about the algorithm. Yeah, so we can't prove things like it produces something that's within a constant factor of optimal even. But it seems to converge to optimal. Like for the regular board, it finds this Ainley thing. It finds like pretty much everything that's in the online encyclopedia. So the online encyclopedia has like solutions, we found all of them. And some other things that meet the bound but don't exceed it. So yeah, it seems to perform well, but we can't really prove anything about it.
There's a question on the YouTube. First, 2 questions. First question is, are there also research on claimable boards?
Oh, I'm glad they asked because we can do that, but we didn't like. Okay, we thought the torus might be kind of too niche already, but yeah, like we can do that. So all we need to do is just alter, at least for the algorithm, it's easy. We just have to change like one line of code for what the hyperedges are, and we'll get some lower bounds. But I don't know if there are upper bounds that are known. We can also use the same approach for the nonlinear program, but we haven't done that actually. So.
And second question is, if the board was a continuous board defined something like a graphon, then is the solution earned by the LP optimal?
Yeah, I guess you have to be a bit more precise what you mean, because then you can do things like set things to be a half everywhere, and yeah, that seems to be the best. Yeah, the best you can do, I think. Yeah. Although, yeah, I mean, I'm not sure the constraints you should have when it's a graphon, but yeah, it's a good question. Yeah.
Why do you set equal half when you're doing the fractional version?
This thing?
Can
Well,
you change that equation so that it's like the sum of everything on the line?
not really. I mean, you can have lots of white things on a line. That's not really an issue.
Yeah, okay.
But yeah, like you definitely shouldn't have, like this is sort of enough if it's an integer program to say there's a constraint, but if it's a graphon, you should probably say something more, right? That, yeah, the number of black queens, like the minimum of those two things, like shouldn't be more than one, right? You can write that as a nonlinear constraint.
So how do you choose the line that you're flipping off?
We
That's
just
randomly.
the one that maximizes like this increase in W, right? So like the app is like, if you go to the app, it's actually solving it like in real time actually. So yeah, like it looks like it might be a lookup of the database, but it actually is solving it, and it's quite fast.
If you don't try to make your solution better, but just switch between different solutions by doing something like swapping, can you have you made some observations that you can translate certain solutions into other solutions?
Oh yeah, reconfiguration
Yeah.
is a thing, right?
Because a lot of the found solutions look way less sorted, right, than other found solutions. And it's unclear whether there wouldn't be a more or less similar solution with respect to numbers
Right.
that is more sorted, that has the queens more in blocks.
Yeah, I mean, I think for some of these, like for odd ends, like, yeah, so some of these solutions I think are unique, but not all of them are. So, yeah, I have to look into it whether you can, like, do this transformation. Yeah.
You can always like translate or something like you just mean what does unique mean? It's up to the trivial symmetries or something.
Yeah, it's up to some trivial, like, yeah, like you can rotate, yeah. By unique, I kind of meant that, yeah, the algorithm just finds one.
I see.
But, yeah, this
So in
is,
some cases it finds more than one.
yes.
Because it starts random, right? So
Yeah.
it might end up converging to different solutions depending on the starting configuration.
Okay. But you've never had it converge to a suboptimal solution. So you
Well,
like if you can find different solution. Well, sorry.
Yeah, this we don't know because like these values were only computed up to, so for the regular board, I think it's known for the first 16, the torus up to the first 12. So beyond that, okay, actually for the odd torus, we computed the answer for 13 as well, but we
But
didn't.
between the solutions your program found, did you have it converge to a solution that is worse than a different solution for the same instance?
Yeah, we just run it many times and take the,
So it does
Take-
converge to local minima,
yeah,
maximum.
yeah, it seems.
Yeah, okay. Any other questions?
Is there any structure result saying that, for example, on the regular board you can put A and black pins and A and white pins so that those two are separated by a line?
Separated by a line. So you want something a bit stronger, I guess, right?
Yes. So on
Yeah, I mean, I think the Ainley construction will be close to that, right? You can sort of chop out just a small part of it, and then they'll be kind of separated by a diagonal, I guess.
another way style put
Where you'll lose like some linear factor, but yeah, you won't lose too much, I think. So.
Just maybe wrong idea, but about the claim ball, maybe placing pin on the claim ball is not good because it is non-oriented. So that vision moving is something weird.
It is something weird, but I think it's, I mean, I guess as long as you define what the diagonals are, which I think you can do.
Maybe mathematically something weird because what is going right upward and between something difference between or then. Oh no, they can sorry.
Yeah, I mean, maybe there's just a way to say it right? Like combinatorially, you can say what the hyperedges are. I mean, you can define this problem for any hypergraph, actually. I think the Klein-Bottle gives you a hypergraph, but yeah, maybe this requires some thought.
So if there's no more questions, let's